In the world of low-altitude UAV reconnaissance, where every second counts and visibility is often compromised by darkness, the fusion of infrared and visible imagery has become a game-changer. These dual sensor systems allow drones to detect thermal signatures, like vehicles or personnel, while simultaneously preserving the fine texture details that visible light provides. The result? A single, high-quality image that enables accurate target detection and tracking, even under the most challenging night conditions. But here's the catch. Evaluating how good a fused image really is has long been a problem, not because we lack metrics, but because the ones we've relied on are fundamentally broken in low-light environments. Take entropy and average gradient, two of the most widely used no-reference metrics. On paper, they seem logical. Higher entropy means more information. Higher average gradient suggests sharper details. But in practice, they fail catastrophically when applied to nighttime, low-altitude scenes. Why? Because in the dark, visible sensors are forced to crank up the ISO to capture anything at all. This introduces massive high-frequency noise, random pixel fluctuations that look just like texture. To entropy and Ag, this noise is detail. So they reward images that are actually full of visual garbage, assigning them higher scores than clean, well-fused images. This is what we call the noise trap, a paradox where the dirtier the image, the better it scores. And it gets worse. These global metrics don't care about where the detail is. They measure the whole image, not the parts that matter. A fused image might have a high average gradient, but if the target is faint, blurred, or lost in the background, it doesn't matter. The metric doesn't know. It can't tell if a small, critical target is visible or invisible. So how do we fix this? The answer lies not in chasing more statistics, but in understanding what humans actually perceive. Enter Target Background Contrast, TBC, a new evaluation metric designed from the ground up for low-altitude, small target scenarios. TBC is inspired by Weber's law, a foundational principle of human visual perception. Weber's law states that our ability to detect a change in a stimulus depends not on the absolute size of the change, but on its relative magnitude compared to the background. A whisper in silence is loud. A shout in a stadium might go unnoticed. The ratio, the just noticeable difference divided by the background level, remains constant. We applied this idea directly to image fusion. Instead of measuring global entropy or gradient, TBC focuses on the relative contrast between a salient target and its immediate surroundings. It asks, is the target clearly visible against its local background? Here's how it works. First, we use the infrared image, the most reliable source for target detection, to generate a binary target mask. We pick only the brightest thermal regions, using a 98th percentile intensity threshold. This ensures we're capturing real heat sources, not noise. Next, we define the immediate background around the target. We do this by dilating the target mask slightly and subtracting the original region, creating an annular ring of pixels surrounding the target. This avoids interference from distant clutter and focuses only on the local context. Then comes the core calculation. We compute the average intensity of the fused image in two regions, the target and its immediate background. The difference between these two values is normalized by the background intensity, giving us a ratio. TBC equals micro-Avg micro-Bg slash micro-Bg plus epsilon. This simple formula is powerful. Because it's relative, it naturally penalizes noise. Add noise to the background. The denominator increases, lowering the TBC score. That makes perfect sense. More background noise means harder to see the target. So TBC correctly downgrades noisy images. But if the target is bright and well-defined, the numerator grows and TBC increases. It rewards visibility. Now let's test it. We created a controlled experiment using synthetic degradation on real low-altitude scenes from the DroneVehicle dataset. We generated 4 cases, an ideal fusion, a target loss scenario, a noisy version, and a low-contrast case. The results are telling. For the ideal fusion, TBC scores highest, 2.185, exactly as expected. When the target is completely lost, TBC drops to minus 0.081, a negative value that intuitively reflects the target's invisibility. That's a huge improvement over Ag and N, which barely register any difference. In the noisy case, Ag skyrockets, nearly 3.5 times higher than ideal, falsely suggesting better quality. N shows almost no change. But TBC drops to 1.974, a clear signal that background noise is degrading the image. And in the low-contrast case, TBC falls to 0.456, again, a monotonic decline that matches human perception. Across datasets, including MSRS, the same trends hold. TBC doesn't just work on one sample. It works consistently, reliably, and intuitively. This isn't just a better metric. It's a new philosophy. Where traditional metrics blindly maximize gradients and entropy, TBC prioritizes perception. It leverages infrared priors to locate targets, models the local background with morphological operations, and computes contrast in a way that aligns with how humans actually see. And it's not just for evaluation. Future work will embed TBC directly into deep learning loss functions, enabling end-to-end training that explicitly enhances target saliency while suppressing noise. We're also exploring how TBC scores correlate with downstream detection performance. Could a high TBC score predict better YOLO or faster RCNN results? And beyond UAVs, the same principles apply to medical imaging, underwater vision, and any scenario where small targets hide in noisy backgrounds. Yes, TBC has limitations. It depends on accurate target detection from infrared input. If the thermal signature is weak or the sensor is poor, the mask fails. And the 98th percentile threshold is fixed. Adaptive methods may be needed for sparse or crowded scenes. But these are not deal breakers. They're invitations to improve. In conclusion, TBC isn't just a metric. It's a step towards smarter, more perceptually grounded image fusion. It solves the noise trap. It rewards what matters. And it brings us closer to building systems that don't just process images, but see them like humans do. So the next time you're evaluating a fused infrared visible image, ask not just how much detail there is, but where it is, and whether the target stands out. Because in the real world of low-altitude reconnaissance, clarity isn't about quantity. It's about contrast. And that's what TBC measures.